వచ్చేప్పటికి అది ప్రోగ్రామ్ కండక్టింగ్ అవుతుందిరా. రికార్డ్ ఇప్పుడు స్టార్ట్ అయింది. సో డిస్మిస్ కొట్టేస్తాను. అప్పుడు స్టార్ట్ అయినప్పుడు రికార్డ్ కొట్టి మర్చిపోవాలి. రికార్డ్ అయినది ఇంపార్టెంట్. ఓకేనా? ఇంకేం చెప్పాలా? ఇంట్రొడక్షన్లు ఎగ్జాక్ట్ 4 o'clockకి అదే వాళ్ళు అయిపోగానే క్వీరీ అడుగు. లైన్లో ఉండి వాళ్ళు మాట్లాడుకుంటూ ఉంటారు. ఆఖరిలో మళ్ళీ వన్స్ అగైన్ థ్యాంక్స్ ఫర్ ప్రజెంటింగ్ అని చెప్పేసి వీళ్ళు ఎండ్ ద సెషన్ అని చెప్పేసి ఎండ్ కొట్టేసి అంతే. ఏం లేదు. నాకు రికార్డింగ్ ఇంపార్టెంట్, ప్లస్ ఏదైనా ప్రాబ్లం రాగానే ఆయన ప్రజెంట్ చేస్తే నాకు ప్రాబ్లం, నాకు తెలిసి ఏ ప్రాబ్లం రాకపోవచ్చు. నిన్న ఏమైందంటే పార్థు సార్, రవీంద్ర సార్ది ఆయన స్క్రీన్ లో మ్యాగ్నిఫై చేస్తున్నాడు, కానీ ఇక్కడ స్క్రీన్ కదల్లా. ఇప్పుడు శ్రద్ధ చెక్ చేస్తే నా ల్యాప్టాప్ లో మళ్ళీ ఆ ప్రాబ్లం రాలేదు. మరి ఇక్కడ పార్థు సార్ వచ్చినప్పుడు మ్యాగ్నిఫై చేయకుండా చేసేదేం లేదు, దాన్ని స్లైడ్ వేరీ చేసుకుంటూ ఉంటారు. ఇలాంటి ప్రాబ్లమ్స్ నన్ను వస్తే ఆయనతో ఫోన్ చేసి మాట్లాడు. నిన్న రవీంద్ర సార్ ప్రాబ్లం మీద వచ్చిందంటే ఈ మ్యాక్సిమై చేసాడు పీపీటీని చెప్పుకుంటూ వెళ్తున్నాడు, కానీ అది ఫస్ట్ స్క్రీన్ లోనే ఉండిపోయింది. ప్రజెంటర్స్ కి ఈ ప్రజెంటర్ కాదు కాబట్టి ప్రాబ్లం లేదులే. అలాంటి ప్రాబ్లమ్స్ వచ్చినప్పుడు మనకి సిస్టమ్ మారమని చెప్పి కాదు సార్, నువ్వు ప్రజెంటర్ కాదు కాబట్టి నీకేం ప్రాబ్లం లేదు. ఒకవేళ ఆయన నా ల్యాప్టాప్ పెట్టి మార్చాడు, నాకేం ప్రాబ్లం రాలేదు. పాదు సార్ ఒకవేళ వస్తే అదే స్క్రీన్ మీద ఉండిపోతుంది. వాళ్ళకి తెలియదు ఆ సంగతి, ప్రజెంటర్ తెలియదు. అటెండెన్స్ కి స్లైడ్ మారదు, మనకి ఒకే స్లైడ్ కనబడతా ఉంటుంది. వాళ్ళకి ఇంటిమేట్ చేయాలి, మధ్యలో చేసి స్లైడ్ మారదు. అదే చెప్తుంది. అప్పుడు దాన్ని ఓవర్కమ్ చేసేది ఎలా? నిన్న రవీంద్రకి అలాగే వచ్చింది. సిస్టమ్ మారండి సార్ అంటే నేను దీంట్లో మ్యాట్లాబ్ ఉంది, దీంట్లోనే రన్ చేయాలి. ఎస్కేప్ నొక్కినప్పుడు ఇంకొక ఫామ్ కనపడుతుంది కదా, ఇటుపక్క స్లైడ్లు ఇటుపక్క పెద్దది కనపడుతుంది కదా, ఆ ఫామ్ లో పెట్టి చెప్పాడు. అవసరమైనప్పుడల్లా జూమ్ చేశాడు స్లైడ్ ని, అలా చేశాడు. కాకపోతే కావాలంటే టేక్ 5 బిగినింగ్ లోనే వచ్చిందనుకో ఆ ప్రాబ్లము, ప్లీజ్ టేక్ ద 5 minutes బ్రేక్ అని చెప్పేసి పాత సిస్టమ్ మారమని చెప్పి ఒకవేళ వస్తే స్క్రీన్ షేర్ చేశారా, పీపీటీ షేర్ చేశారా? స్క్రీన్ షేర్ చేశారు. సారీ ఆఫీస్ ఆఫ్ చేస్తే మళ్ళీ వస్తుంది. స్క్రీన్ లో షేరింగ్ ఇది ఆఫ్ చేసి మళ్ళీ అగైన్ షేర్ చేస్తే వస్తుంది. వస్తుంది కాసేపు అయితే ఓకేగా. సార్ 4కి ఫినిషింగ్ మీరు ఇస్తారా? ఫినిషింగ్ 3కి నేను 5 సార్లు నేను చెప్తాను. నేను మినిమైజ్ చేసుకొని మమ్మల్ని తీసుకుంటాను. మైండ్ పెట్టుకోవద్దు చెప్తా. సార్ స్టార్ట్ చేయండి సార్. కార్తిక్ సార్ రాజేంద్ర సార్, ఏంటి పాత సార్ 2 ఉన్నాయి? నేను కొంతమంది పక్కన రావాలి కదా, ఏమో కొడితే 2 పేర్లు వచ్చాయి, 2ని యాడ్ చేస్తాను. నువ్వేం చేయక్కర్లేదు, ఆయన ఒకసారి లాగిన్ అవుతాడు. ఆయన లాగిన్ అయిన తర్వాత నువ్వు ప్రజెంట్ చేయాలి. ఆయన దేని ద్వారా అయితే లాగిన్ అయ్యాడో మాట్లాడతాడు కదా. ఇన్విటేషన్ పంపించాను. అది దేంట్లో నాకు తెలియదు కదా, 2 పంపించాను. ఆయన లాగానే దాన్ని ప్రజెంట్
లాగిన్ అవ్వచ్చు చెప్పాను. If you want to listen such presentation, sir presentation అంటే లాగిన్ అవ్వాలి కదా. అయినా అవ్వలేదు. ఫోన్ చేసి చెక్ చేసుకుంటాను లాగిన్ అవ్వండి అంటే. Return sorry. Either sir. Either sir. అది పంపించలేదండి సార్ కంప్లీట్ అయిపోయిన తర్వాత కంప్లీట్ అయిపోయిన తర్వాత అదే ఇప్పుడు ఉంటుంది ఫోన్లో డిపార్ట్మెంట్ ఇక్కడ నుంచి సేమ్ మెసేజ్ ఇక్కడ ఇక్కడ చెప్పగా ఇక్కడ దాకా చెప్పు చాలు ఫర్ దిస్ సెషన్ కాదు ఎవరిదిరా స్టార్టింగ్ లో చెప్పాల్సిందిరా ఎండింగ్ లో మళ్ళీ థ్యాంక్ యూ సార్ థ్యాంక్ యూ వెరీ మచ్ ఆన్ బిహాఫ్ ఆఫ్ ప్రివ్లీ డిపార్ట్మెంట్ ఫ్యాకల్టీ మెంబర్స్ వన్స్ అగైన్ థ్యాంక్ యూ అని చెప్పేసి చెప్పు ఫర్ యాక్సెప్టింగ్ దిస్ ఇన్విటేషన్ అక్కడ ఆపేసాయి లాస్ట్ లో ఈ కొంచెం చెప్పాలి ఫస్ట్ లో అయితే మొత్తం చెప్పాలి స్టార్టింగ్ చేసేసి వెళ్ళొచ్చుగా
సార్ మీరు పెద్ద కార్లు నడుపుతారు లేదు సార్. హలో కార్తీక్ సార్ అయిపోయిందా? ఆర్డర్ బాటిల్ పక్కన పెట్టినారుగా.
ఛార్జింగ్ ఉందా?
ఇట్లా పెట్టినా మా దగ్గర ఉదయం ఛార్జింగ్ అయిపోయింది. క్లాస్ నడుస్తుందా సగం క్లాస్ వదిలేసి వచ్చిన నాకు మళ్ళీ ప్రాబ్లం అవుతుంది. ఫైనల్ ఇయర్ ఫుల్ ఛార్జింగ్ పెట్టుకోలేదు. ఛార్జింగ్ అయిపోయింది, క్లాస్ అయిపోయింది సార్. ఏమైంది రెండైందా? చూద్దామా ఎగ్జామ్ చూసి స్టార్ట్ చేస్తారా? సార్ అక్కడ దూకొని పౌడర్ కొట్టుకొని
మీరు ఏం చేయరుగా?
Yeah, hello. Dear participants, good afternoon to all, and welcome to fourth day first session of our STTP. It's my pleasure to introduce today's speaker, Dr. M. Karthik Garu. He received his PhD degree from JNTU Kakinada. At present, he was working as associate professor in the Department of EEE, Bapatla Engineering College, Bapatla. His research is in the area of power quality and renewable energy sources. His focus is on mathematical formulation and analytical solution of problems in power quality and fax devices. He has made significant research contributions on the understanding of the power quality improvement with the help of fax devices by using AI techniques. He is also engaged in department and college level administrative activities, also conducting continuous education program for participants from industry and academia. Dr. M. Karthik Garu published a good number of journal papers in SCI and Scopus Index Journal for his credit. On behalf of EEE Department faculty and students, I thank you very much, sir, for accepting our invitation to act as today's resource person. Now it's the time to hand over the session to today's resource person, Dr. M. Karthik Garu. Sir, please continue, sir.
Thank you, Karim sir. Is my voice audible?
Yes, sir. Continue, sir.
Okay. Is the screen visible now?
No, sir, not yet. Yes, sir. Now it is visible.
Okay. Sir Karim, sir, mute yourself.
Yes, sir.
So good afternoon, everybody. Myself, Dr. N. Karthik, working as Associate Professor in Department of EEE, Bapatla Engineering College, Bapatla. Today my topic is fault data detection in phasor measurement unit based power system with a state estimation. So the presentation outline goes like this. Introduction we will see, then power system state estimation, solution methodologies, weighted least square state estimator and bad data processing, and we will see a case study at the last with MATLAB results and conclusion and references. So when coming to the power system introduction, we generally know transmission system is under stress. Why the transmission system is under stress? Because of generation and loading are constantly increasing, and capacity of transmission lines has not increased proportionally, its capacity is not increased. Therefore, the transmission system must operate with ever decreasing margin from its maximum capacity. So what operators has to do? For reducing that stress, they need reliable information to operate. For performing that operator's reliable information to operate the transmission line, they have to get more confidence in the values of certain variables of interest than direct measurement. And information delivery needs to be sufficiently robust so that key measurements are, even if key measurements are missing, they can deliver that information. And another reason, interconnected power networks have become more complex. Why they become complex means as the more number of loads are increasing, the distribution network is to be increased. In general, planning starts from distribution level. Every electrical engineer knows this. It depends on that, the chain will go up to generation lines. And the task of securely operating the system has become more difficult. So these difficulties are mitigated through the use of this state estimation, because the variables of interest are indicative of what are the specific margins to operate the particular voltage limits and what is the condition of the equipment, we can say health of the equipment and required operator action. So for that variables of interest, these state estimators allow the calculation of these variables of interest with high confidence, despite that measurements that are corrupted by noise and measurements that may be missing or grossly inaccurate. So we will go to the next slide. What is the objective of the state estimation? As we have said on the transmission system, the more stress is increased due to several factors. These objectives of state estimation are, it has to provide a real-time power system condition. Or the olden days, under energy management system, we are having two operational controls. One is distribution automation and is other one supervisory control and data acquisition system, that is SCADA. This is old one. So the state estimation, this supplements SCADA data, that is filter it, fill it and smooth it. And to provide a consistent representation for power system security analysis, we have to get these following things: online dispatcher power flow, contingency analysis, or load frequency control. And another objective of state estimation is to provide diagnostics for modeling and maintenance of the power equipment that are present in transmission system or distribution system. To obtain that best estimate of the state of the system based on set of measurements, the state estimator use the measurements available from PMUs and system configuration supplied by topological processor, and depends upon network parameters such as line impedances and execution parameters such as dynamic weight adjustments. So what exactly the state estimator provides? It provides bus voltages, branch flows, which we will consider in our work as state variables, and measurement error processing results, and it provides an estimate for all metered and unmetered quantities, and filter out small errors due to model approximations and measurement inaccuracies. And it can detect and identify discordant measurements, the so-called bad data. This is what the state estimator provides. This is what the basic process of state estimation, where we will consider the analog inputs here, or by the programming of state flows by using any soft computing technique, that is what called a pseudo measurement, which we will write algorithm or flowchart, that will be given as input to the state estimator. Another one is topology processor and observability analysis, which will give you the output of voltage or theta. If it is a bad data, again it has to be processed. This is what the general cycle of state estimation process in power systems. Generally, how we can define a state in power system? The state is defined as voltage, magnitude and angle at each bus. So that vector Vi bar equal to Vi into e power j delta I, where Vi is nothing but, we know it is a magnitude, and delta is nothing but angles. As you are having some number of buses, it is given x equal to state of magnitudes V1, V2 and so on Vn, and delta 1 and so on up to delta V. So all the variables of interest can be calculated from the state and measurement mode by considering the simple diagram, state x and measurement model h of x, and from that we will get the voltage, power or currents, general variables. We generally cannot directly observe the state, but how we can do that process? We can infer it for measurements, because in measurements generally we are not getting the exact measurements in power system because of the complexity of the network and many disturbances in that power system network. That's what they have mentioned here: gross measurement errors and communication channel outages. We will consider here a simple load flow example, a 3-bus DC load flow, where here 3 buses are considered, bus 1, bus 2 and bus 3, where this is the actual flow. 65 megawatt is there. From bus 1 to 2 it is 60 megawatt. From 1 to 3 you are having 5 megawatt, where input is given at the 3, 35, 35 plus 5, 40, 40 plus 60, at the output of the bus 2 you are having 100 megawatts. The only information we provide about the system is provided by 3 megawatt power flow meters. M12 is a meter located between first bus and second bus. M13, here it shows the meter location, where M13 is located between bus 1 and 3, and M32, that is a meter that is located between bus 2 and 3. And it is having the per unit reactances on 100 MVA base. X12 is given by 0.2, X13 is 0.4 and X23 is 0.25. A simple system is considered, and we will see this system, if correctly the meters are readed, what will be the angle measurements and voltage magnitudes, and any errors in meters are there. If we consider any errors in meters, how the power flow changes, that we will see in next slide. So see, out of 3, if we know 2 quantities, the other things can be easily calculated. So M13, it is 5 megawatt as per the previous column, that is 5 divided by 100, 100 MVA base, you are getting 0.05 per unit, and M32 is 40 megawatt, that is 0.4 per unit. So here I am calculating a function F13 equal to, this is nothing but a part of the DC load flow, where it can be represented as some B into theta. What is P? Nothing but 1 by X, susceptance. 1 by X into theta 1 minus theta 3 is 0.05 per unit. Okay, P equal to Bx. It's a general DC load flow. From that, what I am calculating? Theta 3 is 0, where one of the bus we will consider as a swing bus. Now calculating the angles by considering in that equations where theta 3 equal to 0. If theta 3 equal to 0, we will get theta 1 equal to M13 into X13, where X13, we are having this value as 0.4. So 0.4 into 0.05, where you are getting theta 1 as 0.02 radian. Like that, if we calculate theta 2, you are getting the angle change is minus 0.1 radian. These are whenever the meters are readed correctly. Next thing, we will see the case here, second case, with all the meters having some small errors. Where see the meter is, first meter is having, suppose it reads 62 megawatt in per unit 0.62, M13 6 megawatt and M32 0.37. And by using only M13 and M32 readings, as per the previous calculations, considering the same swing bus theta 3 equal to 0, we will get theta 1 as 0.024 radian and theta 2 as minus 0.0925 radian. So what is this results in the system? Predicted match flows that M13 and M32, but the flow on the line 1-2 does not match the reading of previous reading 62. So this way, if any change occurs in any part of the power system, there may be an error in the power system. These errors that we will measure with the help of the state flow, and then later in the part of our network, we will consider state flow with phasor measurement unit, where it measures directly the voltage and a change in angles such that it can accurately measure that PMU device, where with the help of that V and theta's total load flows in terms of a digital quantity before the fault or after the fault. There are many advantages of PMUs where if we know all that quantities, we can design exactly the power system and stability of the power system is maintained, and where exactly the fault is observed or not, or what is the fault diagnosis. Many advantages are there with PMU by the help of the state estimation with PMU. That's what our main intention of this total presentation. So that's what we have said here. The only thing we know about the power system is measurements to estimate system conditions. Measurements are used to calculate the angles, what I have said. It is given in the conclusion part where the loads and generations can be calculated. We will call here voltage angles as the state variables for the 3-bus system, since knowing all our quantities to be calculated. If we can use measurements to estimate the states of the power system, then we can calculate all the power flows, generation and so forth, what we can decide. The state estimation means determining our best guess at the state. We need to generate the given noisy measurements, and this leads to a best estimate of unknown parameters. The traditional methods are given like this: maximum likelihood and weighted least square method, and non-traditional methods are evolutionary method, genetic algorithm, differential algorithms, etc. But what we will concentrate in our research work is the weighted least square method, which is the better method of all as compared to all the traditional methods. This is what the measurements are assumed to be in error, where suppose if Z measured is the measured value and actual true value of the quantity being measured, then we can generate some random error, then mathematically it can be expressed as Z measure equal to Z true plus some error eta, random measurement error. So we are coming to our exact method, what I have said, this weighted least square approximation. See, the problem of state estimation is to determine the estimate that fits the best measurement model. So here we are considering an M-bus electric power network, which is denoted by X, having a dimension of 2M minus 1, which is comprised of M bus voltages and M minus 1 bus voltage angle. Slack bus is taken as reference. Generally, we will consider slack bus as reference. The state estimation problem can be formulated as minimum J of X equal to, the expression is visible to you, sigma I equal to M to M, where M is the number of buses. Zi minus Hi of X whole square divided by sigma I square, where Z is the measurement 1 and measurement vector. Here it is given Z is the measurement vector, H is the measurement matrix, M is the number of measurements and sigma square is the variance of the measurement, and X we have to calculate vector of unknown variables to be estimated. The problem is defined as unconstrained minimization problem. This efficient solution can be used basically on Newton's method. That Newton's method we will see by Taylor series expansion. H of x plus delta x is given by H of x plus H of x into delta x, where the Jacobian matrix capital H of x is given by dou H of x by dou x. Then by that least square objective function is given by that big expression. It is a mathematical expression which will be available in all the textbooks. J of delta x equal to half into Z minus H of x. Okay, where R is the weighing matrix, where it is internally, those are variance squares. Sigma 1 square and so on, sigma m square. From that, J of delta x is given by half into E of x, where from this Z minus H of x, we are considering here E of x. That expression they have changed here, E equal to Z minus H of x, which is the residual vector. Then some slides I have placed it here. For getting that least square method, I am differentiating that with respect to x, where you are getting minus H transpose R inverse E minus H into delta x equal to 0. From that, if I multiply and equate on both sides, finally we are getting a matrix equation called as G into delta x equal to H transpose R inverse into E. What is G here? G, you can directly see H transpose R inverse into H, which is called gain matrix, where it is a sparse, positive, definite and symmetric provided that system is fully observable. So we will consider an example here, weighted least square. The full scale reading of the meter will be 100 megawatt and meter accuracy is given plus or minus 3 megawatt, that is equal to 3 sigma, and then sigma is equal to 0.01 per unit. As it is a 3-bus system, we will consider 2 estimates and one of them is a slack bus. That's why here it is mentioned directly. The third bus is assumed as a slack bus. Then the number of state variables are 2, which is given as x estimate equal to theta 1 estimate, theta 2 estimate. Here these are considered as angles. In the next example, what we are going to see, by weighted least square, the x is taken as voltages. So 2 examples I consider here. So to derive the H matrix, we need to write the measurements as a functions of state variables theta 1 and theta 2. Previously, we have seen the same thing, f12 equal to 1 by 0.2 into theta 1 minus theta 2. That is nothing but 1 by 0.2, 5 theta 1 minus 5 theta 2. Then we are writing power flow through 1, 3 and similarly 3, 2. So you are getting these equations, where from this I can design a matrix called as H, where H is nothing but coefficients of 5 minus 5, here 2.50 and 0 minus 4. Like that you will get this equation, H5 minus 5, 2.50, 0 minus 4. Then the covariance matrix is given by sigma square M12, M13, M32. Only 3 buses considered here, covariance, and that variance is given as 0.00001, 0001 and 0001. Our d square approximate method, the formula is given by theta 1 estimate equal to, this is G inverse. What is G? H transpose R into H whole inverse, again H multiplied by R inverse into this powers 0.62, 0.06 and 0.37. So if I multiply all these things, you will get the value of theta 1 estimate and theta 2 estimate calculated 0.028 and minus 0.094. So from the estimated phase angles, we have to calculate the power flow in each transmission line, and the net generation at each load bus is given by the function J of theta 1 theta 2 equal to, this is the original function, Zi minus Fi square divided by sigma square, what I have shown in the previous slide. So from that they are writing 0.62 minus 5 theta 1 minus 5 theta 2 whole square by 0.0001 and so on. So you are getting this Jacobian as 2.14. So this is one example, and that example they are showing in pictorial diagram here. See the angles they have written here. Theta 1 is 0.025871 and theta 2 is minus 0.094286. This is solution of weighted least square example. We will consider next part of our system. What is exactly means bad data. Bad data means essential functions of state estimator is to detect measurement errors and to identify and eliminate them if possible. These measurements may contain errors due to, see in our labs also, whenever we are measuring the quantities, in meters we will get some errors. To consider that errors and to exactly portray whatever the exact flow value in that part of the network, again we have to check the error for that meter and we have to make error for that meter 0 and we have to restart the experiment. That means we will calibrate the meter there. So, but in big power system network, the process of calibration is not possible because all will go under dynamic conditions, right? Because if there is a load change or any problem in the power system or a transient conditions occur like this, every part of the power system performs major happiness. So that random errors usually exist in measurements due to the finite accuracy of the meters or telecommunication medium. This is what we call interference. This bad data may appear in several different ways, depends upon the type, location and number of measurements that are in error. They are broadly classified here. Single bad data, only one measurement in the system creates a large error. We will call it as a single bad data. Multiple bad data means more than one measurement will be in error. And some definitions are also given here for your reference way. Whenever we are calling a critical measurement is the one which is observed from the measurement and will result in an unobservable system. The measurement residual of critical measurement will always be 0. Okay, then we can say when the system is observable, if all the state variables calculated with the available set of measurements, we can say the system is observable. And when we can call these definitions or terms will come across whenever you are searching the state estimation with phasor measurement units in power system in IEEE or Springer or LCWare papers. Lot they will talk with critical measurements and these things. Redundant measurement means the measurement which is not critical. That means if it is not 0, then we can call a redundant measurement. That's what they have said here. Only redundant measurements may have non-zero measurement residuals. That means they will create an error. So critical pair means if that sort of two redundance occur, then we can call them as a critical pair. Two redundant measurements whose simultaneous removal from the measurement set will make the system unobservable. That means we cannot identify the error, but it creates a disturbance in the power system. Those are called critical pairs. So how can we identify whether that is a particular data is measured as a bad data and identification? It is having some mathematical calculations. So see, first we have to measure that particular data. Identification is the process, and bad data can be detected. It has to be removable, and single measurement means if it is not critical, already it is set here. This is what the important steps for the detection of the bad data. We have to make the raw measurements from the system to determine the weighted least square xi. Then substitute the estimates in the equation xi, where z cap measurement matrix is given by some h into x cap to calculate the estimated values of zi cap, and hence the estimated errors is ei cap equal to zj minus zi. Then evaluate a weighted sum of squares f cap equal to sigma j equal to 1 to m. These are all mathematical formulas available anywhere, what I have said previously. A square divided by sigma square. 1 by sigma square can be written as some weighted matrices also. Later in the next coming example, I will show you how to detect the bad data. If that particular tolerance is less than our critical value corresponding to alpha, this with k degrees, this is assumed by chi-square distribution. A table is there, I have not mentioned here. With that table, we will fix the tolerance. If that is less than that particular tolerance, your data is not bad data. Whatever the error, if you are getting, it is more than this tolerance value, then you can identify that particular measurement in that part of the network is a bad data. Okay, that's what they have said here, and state estimations are accepted as being accurate. For a non-critical redundant measurement case, that means if it is not zero, then we have to flow for the standard deviation, where the vector normal residuals are calculated as RII. These are all mathematical expressions. These are the steps to bad data identification, the continuation of previous one. We have to solve the weighted least square estimation, where EI equals Zi minus H of x, and compute the normal residuals EI by square root of RII. Then find the peak measurement, where EP, if it is longer than C, the peak measurement, that's what I have said, C. This C is nothing but the tolerance against. This C is the tolerance. There they have taken K. In other papers, they may mention this as C. The peak measurement will be suspected as bad data. Else, stop node bad data will be suspected. Here, C is a chosen threshold. For instance, they have considered here some 3. Estimate the peak measurement from the measurement set and go to step 1 if it is not. So see, this is the important example where we are considering in this part of presentation, where V1, V2 are the state variables here. This X cap. That means I have to estimate this V1, V2 if I am having the measurements of Z1, Z2, Z3, Z4. Z1, Z2 are 2 ammeters, nothing but current measurements, and Z3 and Z4 are voltage measurements. And they have given some weightages here, W1 equal to, any estimates and in the chapter, W1 equal to W2 100, W3 equal to 50, W4 equal to 50. Then we have to estimate the voltages V1 and V2. Here V1 is not there, we have to put V1 and V2. We have to calculate that voltages V1 and V2. For that, what we will do is, by the same network analysis, we will write the equations here, nodal equations. We will write the nodal equations, and I will formulate Z1, Z2, Z3, Z4 in terms of the voltages. Previously, the voltages are nothing but here, X1 is V1 and X2 is V2. By considering them as state variables, I will express Z1, Z2, Z3, Z4, 4 equations in terms of V1, V2, and I am adding directly the error here. I am thinking that error will come in that measurement. So measurement equations, because see, in nature, every meter is not ideal. We cannot get exact zero error, right? That's why what they have considered in the measurement itself. Measurement equations characterizing the meter readings are found by adding error terms to the system model. That's why we have derived already this thing by the normal analysis, where I am getting all these equations, Z1, Z2, Z3, Z4, in terms of X1, X2, 5 by 8, 1 by 8, all these are coefficients of the voltages. You remember here, X1, X2 are nothing but voltages. And Z1, Z2 are current measurements, Z3 and Z4 are voltage measurements, and E1, E2, E3, E4 are corresponding errors added to that particular measurements of the meters. So then forming the H matrix. In the previous example, H is considered 1 by 5 into theta 1 minus theta 2. Like that, here H matrix is nothing but coefficients of this state variables V1 and V2. Nothing but here x1 and x2. That means 5 by 8 minus 1 by 8, minus 1 by 8, 8 by 8, 3 by 8, 1 by 8, 1 by 8 and 3 by 8. Like that, we will form the H matrix from the previous equation where this H matrix. And so R inverse is nothing but here W. In the presentation, it is not mentioned exactly in the problem itself W, but whenever you are solving, you will get confused. That's why we have mentioned here this R inverse is nothing but weighted matrix, that is 100, 100, 50, 50. Suppose if you want R and కావాలనుకోండి దీన్ని sigma square అవుతాయి అంటే inverse అవుతుంది 1 by 100, 1 by 100, 1 by 50, 1 by 50. Those are nothing but sigma square, variance square. And here Z is nothing but the measurements what you are getting. Some error measurement 9.01, 3.02, 6.98 and 5.01. In the problem itself they have mentioned Z1, Z2, Z3 and Z4. That measurements I have considered here. Where G is called in the next slide, we are supposed to calculate G. For your reference sake, again I have mentioned here G. What is exactly G? H transpose R inverse into H. See, H transpose is, we have to transpose for this. R inverse is nothing but this matrix. And H is again this, because see in the next slide they will mention directly. That's why for easiness sake and for future reference, if anybody refers this PPT, they have to get the clear understanding how exactly the G is calculated. So solving for estimates, this x1, x2, nothing but again they are represented here. See in the next equation, I have portrayed here x. X is nothing but x1, x2, that is v1, v2. It is solved by G inverse H transpose W into Z. What is this G inverse? H transpose R inverse into H. Okay, after substituting and calculating all these things, we will get V1, V2. These are easily calculated by MATLAB. No worries here. If you mention all the matrices, just simply star mark and multiply all the matrices, 4 matrices, you can get directly this result, V1 cap, V2 cap, that is 16.0072 and 8.0261. These are the voltages we are getting here. So that voltages, keep it there, and estimated measurements are calculated here. Z cap equal to H into X cap. What is H? We know already H, this one. And X cap is nothing but this. That's why I have mentioned there. X cap, some persons may get doubt what is X cap. X cap is nothing but these voltages. So these voltages multiplied by that measurements H into X cap, you will get this estimated measurements Z1 cap, Z2 cap, Z3 cap and Z4 cap. Then estimated error is calculated by we have seen this equation already, Zj. What exactly the meters that will measure minus our estimated measurements using weighted least square method. So E1 cap, E2, E3, E4 equal to, you are subtracting this Zj minus Zi, you are getting some errors here, 0.008, 00456 and 0.2569 and 0.00070. Then see, we have to go for this Chi method, Chi square method. I'm assuming it is given in the problem itself, alpha equal to 0.01, number of measurements are 4 variables and number of state variables are 2, then the degree of freedom is this 4 minus 2, that is you are getting 2. So from CHI square PDF, we'll get x square equal to xk square equal to 9.21. Then from this, we are evaluating the weighted sum of squares. F is EI square into sigma I square. I have said already 1 by sigma I square is nothing but this weighted matrix. So 100 into these errors, 0.00877. It is a tedious mathematical process every time involved in the power system. 100 into 0.008, all the equation I have written. And then if you solve that, we are getting this F cap equal to 0.043507. See, this factor is less than 9.21. Correct? Whatever the tolerance that we have got from the table. So we can conclude that 99% confidence that there is no bad data here. That means error is very minimal. Then what we can see in the next slide is, we will consider the error part here. Initially the meters itself we will consider, the raw data we will consider, and from that we will calculate, and by changing the 4th meter, that is V4, we will consider 4.4. Now suppose the raw data measurements that is considered Z1, Z2, Z3, Z4. Suppose 9.01, E3 correct 9.01, 3.02 and 6.98 and 4.4 instead of 5.2 previously, we are considering here 4.4. Now whatever the procedure we have solved, previous ka chesinanta cheyalandi. Now calculating the estimated error similar to the above, using the new measurement, we are getting E1, E2, E3, E4 cat transpose as 9.01, 3.02, 6.98 and 4.4 transpose. Now evaluating the weighted sum of squares f cap we get. Sorry, 100 into 0.06228. If this 0.06228 is calculated like this, ilane తీసుకోవాలి మళ్ళీ 9.01 minus that calculated value. If you calculate that, ఆ స్టెప్స్ అన్ని మళ్ళీ చేయాలండి. ప్రీవియస్ 3 స్లైడ్స్ చేస్తేనే ఈ వాల్యూ వస్తుంది. 0.000877 square for first one, second one, third one and fourth one. Fourth one చూడండి error 0.00070, previous గా వచ్చేసి -0.00070. So here previously it is 0.00070, but for 4.4 here we are getting 0.4928. So that means what is my weighted least square error here, f cap? We are getting 15.1009. Since 15 is greater than 9.2 or not. So as it exceeds one of the value of threshold, so that means in that particular meter it is creating some nuisance where exactly that calculated value or the measured value of 4.4, it is not exactly meeting that 5.2. Some error is there. So to minimize that error, we have to follow some procedure here, that is standard error estimates are now see, all this is for computer process. మనం చేసినంత కంప్యూటర్ ప్రోగ్రామింగ్ లో ఉంటుంది. ఆల్రెడీ ప్యాకేజెస్ ఆర్ అవైలబుల్ with this programming, where in the substation data with help of the state estimation and PMUs, nowadays totally they are calculated with the help of the PMUs only. But what exactly that happens beside that PMU and state estimation, my PPT is covering that important process. How exactly that state estimation process goes, how exactly that bad data collection, whether it is a bad data or good data. And we will take some case studies after this slide. So RII is that formula, identity matrix minus HG inverse H transpose R inverse into R, where the largest normalized residuals are calculated using this EI by square root of RII. ఈ RII ప్లేస్ లో వేస్తారండి. నెక్స్ట్ RII మీన్స్ చూడండి 1 minus this 807 is nothing but HG inverse H transpose R inverse, that calculation, multiplied by R is 0.01, 0.01 for first two cases, and for third and fourth case these are 0.02 and 0.02. So from these normalized errors, E1, E2, E3, first three quantities are positive, where from the standard value you are having negative value. So whenever you are getting in these normalized residuals, one of them as negative, we can say that the measurement Z4 is a bad measurement. Then that measurement is removed from the measurement set. And we will not remove exactly that value. We have to replace that particular voltage measurement meter. Our meter ni marchukotam gaani edanna cheyali. Like this, we can easily estimate from the complex network by feeding that all the voltages and powers to this simple set of program directly, where exactly that bad data is there. It depends upon the calculation of the threshold value. It will give you that bad data indication itself in the program. So the case study here we are considering, first we will calculate all the state voltages and state voltages only in non-linear phase, and then those are transformed into PMU data after the post processing stage, and then we will combine the state estimation with PMU. That's what this is totally said here. The method for predicting the state is taken as state estimation. In the past measurements, only again the introduction is came here. Measurements could only provide the magnitude, but a PMU device is currently used where both you can measure voltage and phase angle of the particular situation or current phasors also with the associated lines. As a result, phasor measurements are replaced in conjunction with other measures to determine the condition of the power system. So what is our major goal of this work is to establish and assess the hazards that this fake data injection attacks provide to PMU devices. That means if you are getting a fault data, that means CP has to open at particular time interval, and suppose that breaker is opening prior to that or after that also, it results in malfunction of the particular breaker. Like that, there are many instances where you can quote many examples where the particular data for relaying or breaker switching operations, if the data is not exact, the breaker doesn't know. Simply it is a switching action, depends upon the sensing device relay. That's why we have to priorly access that particular values and we have to give the values precisely the information to the end user, that means substation people, or to the breaker, such that where they can isolate the faulty system exactly. And after that faulty system, the data can be stored in the system where it can be analyzed by the next supervision engineers, or in future also, suppose say some 2 years back or 1 year back or 1 week back, what exactly happened in that part of the power system, all the data can be restored with the advanced PMUs. On India lo kuda chestunnaru adi, where it is called as WAMS anukuntandi. Some expression is there, wide area monitoring system. With the help of the wide area monitoring system and the synchronized PMUs with state estimation on government in the 5 grids, I think according to my scene in the Google, in the northern region, I think in the northern region, they are supposed to plan some 1187 PMUs with 350 measurement sets, and later they are planning to control or observe all the 5 regions of the grids. Because see, in our India now, the present capacity is in terms of gigawatts loki వెళ్ళిపోయింది power consumption అనేది. So it depends on that. They are planning this wide area measurements, wide area monitoring system. Okay, so here we are in our case study. For example, I have considered here the standard IEEE 14 and 30 bus system, and we have analyzed that state estimation without PMU and with PMU, and then the use of the PMU measurements to estimate the condition of a power system. Okay, this is what the basic, everybody knows a power system engineer, difference between a transmission and distribution systems. It is a mesh topology, and in transmission it is a unidirectional power flows and balanced lines and loads. But in distribution we majorly use radial topologies and bidirectional power flows, and you're having unbalanced lines and loads because load is customized. We cannot demand the customer to use only this particular type of the load. So some loads may create disturbances in the power systems also. Then attributes, and what are the parameters that will replace the SCADA units with the help of this PMUs means, in the point of measurement point of view, SCADA will give you analog, but PMU it is a digitalized quantity. In data processing, it is SCADA 2 to 4 cycles per second in olden days, but PMU 60 cycles per second. Observability point of view, SCADA it takes only the static, not in a dynamic position. The meaning of dynamic means in live operating conditions, this phasor measurement unit can give you the voltages and angles exactly, and monitoring it only wherever exactly the RTUs are considered. The SCADA will take the data from remote terminal units and it will monitor only local. But PMU, with whatever I have said, WAMS, wide area monitoring system, depends on that wide area monitoring system, and by the installation of this PMUs, it can monitor some heavy distances of the transmission networks also. In magnitude and phase angle with the SCADA it is not possible, but with PMU it is possible. And post fault monitoring system, so because in SCADA only it will give you the particular location and it will switch off, but in PMUs it will analyze the data with the help of, I will show you now the diagram of PMU, how far sophisticated that PMU is. But the PMU is invented in 1980s itself. This is what the components of PMU. You're having analog filters, anti-aliasing filters, and this data is converted to 16-bit analog to digital converter, and to a phasor microprocessor is given, where here the step of this voltages and angles can be done. And this phase locked oscillator is used for the sampling of this particular A to D converter. And GPS, it has to provide the time synchronization frame. That means exactly at which particular point of time your fault has occurred, and all that analysis of day, year, all the data is given by the synchronized measurements, that is GPS receiver, and is connected to the modem for the transfer. And wherever the engineer requires from other part of the data also, he can simply access from the database. This I will explain in the form of a theory here. So see, analog inputs, the main components I have listed here: analog, GPS receiver, oscillator, A to D converter, anti-aliasing filters, phasor microprocessor, and modem. This is what I have said already in the theory. These analog inputs, where they can come from, these will come from potential and current transformer secondaries. They will give you the voltages and currents. That's what it is mentioned here, analog inputs. And anti-aliasing filter, it is basically a low pass filter, where it cuts out some of the frequencies. If any noises are there, that will be smallly reduced here. But internal non-observable noises cannot be decreased with the help of PMU. And phase lock oscillator, as I have said, for getting that exact time frame of reference with GPS, they are providing that GPS is also where it exactly needed high synchronized stamping, and GPS is a satellite based system for providing that position and time. Exactly that purpose only that phase lock oscillator is given. And this A to D converter, everybody knows, we are already studied in subject itself. It converts analog to digital signal, and required rate is given there, and rate of values are sampled is called sampling rate of the converter. And GPS, again it is mentioned, synchronized time is given, and some history of GPS I have mentioned here. The first GPS was developed by United States, and it consists of 24 satellites in 6 orbits at 10,000 miles above the surface of the Earth. Thus, half of the altitudes corresponding to geosynchronous orbit. In addition, the satellites in paper IJERT, some journal paper I have copied this matter. Everybody can get this matter of this GPS information, where they can transmit one pulse per signal, and GPS satellites provide a very accurate time. This means that what we require is in our voltage and power system recordings from different substations can be directly displayed, voltage and current readings on the same time axis and in the same phasor diagram. So see how much advantageous is this. And this microprocessor, where they are using the DFT techniques, and with the timestamp is created from the GPS, and timestamp identifies the identity by using that universal time coordinated UTC times. Generally they will mention that UTC time. And modem, it is a general carrier which modulates some signals, and it can demodulate also. Some transformation device, nothing but modem is a transformation device. The objective of the modem is to produce signal that can be transmitted and replica of original data. These modems can be used with no means of transmitting analog signals. Okay. This way the PMU is installed in live diagram I have got. See from current transformer secondaries from the PT and CT, all with the help of attenuators. That means that by decreasing that values, not decreasing means they will not bury the original values. Whatever exactly required by the PMU, for that they will decrease, and any attenuator means any spikes are there, that will be decrease that noises and given to the phasor measurement unit. And whatever the top right hand side is given as indicated as modem, and it is linked with the computer. So this is what state estimation using phasor measurement units. The method what you are using PMU measurements are insufficient. Only PMU cannot do everything. So that PMU data has to be got from state estimation data. That's why we are saying here the accuracy of state estimation is much enhanced when phasor data are added to additional measures in adequate quantities. As a result, there are multiple approaches. Several number of approaches are there for incorporating that phasor data into standard measurement. But here we are using appending this PMU of active sources to the usual measurement set is a simple solution, because a lot of softwares are developed on this way only. The consequential state estimate is non-linear, deciding considerable changes to the current EMS software. EMS means energy management systems. Another option is to keep the standard state estimation software in place, but use a post-processing linear estimator to incorporate the phasor measurements and classic state estimator results. So we have said there are major approaches are there where EMS capabilities can be done, where state estimation is what we have discussed up to now, VN data, unless they are converted into equivalent PNQ measurements. One of the most successful and efficient method is phasor measurements is used in the post-processing step. That means in the prior data, for bad data selection, they will use state estimation, and later they will append. Appending means adding that state estimation data with the phasor measurement unit data, and they will finally calculate with the threshold error. If the threshold error is less than that particular chi square distribution, then we can say there is no bad data. If it is greater, then we have to calculate that normalized error, whatever the formulas I have provided there, and then they have to choose that particular bad data, identify that particular bad data, and they have to change that particular bad data or the meter. Some repair work has to be done at that particular place. So in this approach, phasor measurements are included after a post-processing step. See, in the first technique, what I have said, that weighted least square approximation method is used to extract state variables and state vector from the weighted least square approximation measurement vector are represented in XY plane. In the second operation resulting in new measurement, a linear model based technique that doesn't require any iterative approach is considered. This is what the country's first PMU at CPRI Bangalore. Some one diagram I have gathered from the net. And this is what according to IEEE systems, how many PMUs we have to use for 14 to 30 bus system and number of chips where exactly they are using. This is what we have done the work on this 14 bus and 30 bus system. We have developed a program for this 14 bus and 30 bus system where the PMU is located, and exactly at 7489, suppose if the data is mismatched there, compromised measurements for 14 and 30, we have got the results like this. If you can observe, for 14 bus system without PMU, we are having at the first bus 0, at the second bus some 0.5 error, and from the 4, 5, 6 up to 14 bus, the error is maintained at 1.5. But whenever you are using this laser measurement unit, the error, it is decreased. See, at the second bus you are having 0.5, but at the second bus with PMUs, the noise will be decreased like this. That means it will give you exact values of voltages. And error తగ్గించదండి. PMU is nothing but a device which measures the exact value of voltage. State estimation తో మీకు ఇంత error వస్తుంటే, by using this PMUs, the exact value of the voltages at that particular bus is measured, where that error is decreased by this component. That's what you have to understood from the graph. Okay, error ఇంత తగ్గుతుంది అంటే PMU doesn't actually decrease that particular error. What it does is, it will exactly measure the value. So where we have plotted is this angle estimation error. These are angle changes. 0.04 like that. From 5 to 6 to 14, here it is 1.5, but here it is made exactly 0. That means from 6 to 14, the PMU measures correct data in angles. Then the same can be done for 14 bus system in magnitudes. We compared here, and we have got the values. The same process when you compare these two graphs, you can see that magnitudes measured here from 6th bus. Suppose you take 6th 5.2. If I inchi vesarlendi graph wheel in the MATLAB, from 8 it is 5.2, but 8 you are having from 6 to 8, the magnitude is constant. That means the PMU exactly measures the voltage from 6th bus to 14th bus. The same we have done for 30 bus system also. 30 bus angle estimations, first slide, and the next slide we will go for this with and without PMUs. This is angle estimation and this is magnitude estimation. What we will conclude is, the real-time monitoring and control of power systems is extremely important. The state estimation becomes the backbone. So in this environment, a real-time model is extracted, nothing but IEEE 14 and 30 buses, and we have estimated the nodal voltage magnitudes and phase angles by considering all the input data of all the buses, transmission lines, whatever those are connected in that 14 bus system and 30 bus system. And state estimation results can be improved by using accurate measurements like PMUs, and traditional state estimation and bad data processing is reviewed. These are the references. I'll show you the MATLAB execution. This is what the MATLAB for 14 bus we have placed the program. For 14 bus, if you see, means you'll get exactly whatever the figures I have shown here. Suppose if I change the program to 30 bus system, if I run the program, whatever the graphs I have placed in the PPT, you are getting estimation errors with PMUs, voltage angle estimation, these two shows, and magnitude estimations with PMUs. Okay. Thank you all from my side.
Once again, thank you very much, Dr. Karthik sir, for accepting our request.
Thank you,
Share
sir.
the knowledge.
Thank you, sir. Thank you very much.
Adisarthi sir, are you there? Hello?
Yeah, Karmila, you can
Yes, yes. participants, once again good afternoon to all and welcome to fourth day second session of our STTP. It's my pleasure to introduce today's speaker, Dr. J. Parthasarathi Garu. He completed his MTech from SVU University Campus, Tirupati, and PhD from JNTU Hyderabad. At present, he is working as assistant professor in the Department of EEE, Bapatla Engineering College. His research in the area of fax devices, power quality, harmonics measurement, wavelets, fuzzy, and fault identification. He taught different subjects at BTech and MTech level students. Dr. J. Parthasarathi Garu is a life member in various technical bodies like ISTE, IEI, and in others. So he has published a good number of journal papers in most reputed journals and has good number of conference publications also. So on behalf of EEE department, faculty and students, I thank you very much, sir, for accepting our invitation to access today's resource person. It's time to hand over the session to today's resource person, Dr. J. Parthasarathi, sir. Please continue.
Thank you, Karmala sir.
Thank you.
Am I audible to the participants?
Yes, sir. It is audible.
Yeah, can I continue?
Yes, sir. You can continue.
Good afternoon to Ananda. Myself, J. Parthasarathi. I am working in the Bapatla Engineering College from the last 12 years. Really, it is privilege to me to talk in the program, that is faculty development program. So today, I would like to talk on impact of harmonics on power quality. So everybody knows what are harmonics in BTech level or MTech level. Even in research area also, we are doing a lot of research on different harmonic mitigation techniques as well as different harmonic measuring methods. So anyhow, we'll start the session. So in this session, I would like to discuss the introduction, harmonics, what are the types of harmonics, what are the potential sources of harmonics, effects of harmonics on main supplies, standard of harmonics, what are the different techniques in harmonic measurement, and what are the harmonic mitigation techniques, a simple case study, and it also will conclude with this. So as you know, before discussing the harmonics, it is very much required to know about the power quality, because harmonics also is one of the part of power quality problems. According to utility, what you can say is power quality is nothing but reliability. How far it is reliable. So quality of power means so how far it is reliable. Whereas in terms of load aspect, it is defined as the power supplied for satisfactory performance of all equipment, that is all sensitive equipment. Since we are having different loads from domestic to the different consumers, industrial consumer, agricultural consumer, whoever it may be. So they need their equipment should be perform satisfactory operation. So this depends upon the end consumer. According to end user point of view, it is defined as any power problem manifested in voltage, current or frequency deviations that result in failure or misoperation of customer operation. So everybody having their own meanings. I mean, so load having one meaning. So similarly, endpoint consumer having its own definition. So while we have certain standards like IEEE dictionary, power quality is defined as the concept of powering and grounding sensitive equipment in a manner that is suitable to the operation of that equipment. Whereas one more body, which is IEC, International Electrochemical Commission, which is defined as set of parameters defining the properties of the power quality as delivered to the user in normal operating conditions in terms of continuity of supply and characteristics of voltage. So IEC has taken two constraints mainly. So whereas he considered the continuity of supply along with the characteristics of voltage which includes magnitude. So single phase consumer he requests 230, whereas frequency 50 Hz, right? So everything he has considered. So these are the two different bodies having. So the output, I mean, so the the requirement of either IEEE or IEC standards, the meaning is same. So as per this is as per the IEEE document, so which is according to 1159 2009 IEEE. So it is
Sorry to interrupt you. The slide was not moving, sir. Okay, now it is okay. Okay, sir.
Check it once, please.
Now you are in fourth slide, right?
Yeah.
Okay, sir. 1 second. Check it. Just change the slide, sir. 1 second.
Check it once. Okay. Check it once.
Okay, sir. Now it's moving. Okay, sir. Okay, sir. Now it is okay. Continue.
So according to the power quality, so different problems we are having the different problems. So one among that is over voltages, under voltages, harmonics, flickers, unbalance, sag, swell, transient, interruption, frequency deviations. So according to IEEE, these are the main sources and which are causing the problems to the power quality. So in that we will discuss one before discussing about the harmonics. We need to discuss about the other power quality problems too. This is very much required. So in this context, so we are having over voltage and under voltages. So the power quality problems always they are described and their characteristics always discussed with respect to the time, which means how long they occur, whether it is a 10 second or 1 minute or 2 minutes. So likewise, you can over voltage is nothing but so if it is equipment nominal operating voltage, so this is more than the nominal operating voltage, but which occurs more than 1 minute of time. Whereas under voltage is nothing but so which should be less than the equipment nominal operating voltage. If it should occur for at least more than 1 minute of time. So for a single phase consumer, 230 volts we are expecting. So rated voltage is 230. So if it falls below 230, it means 180 or 200. If it is more than 1 minute of time, it is said to be under voltage. Whereas we are expecting 230 volts of supply only. So 250 or 270, if it occurs for 1 minute of time or more than 1 minute of time, it is said to be over voltage. So as we already know, different over voltage is mainly due to over voltage or under voltage. It may be due to sudden load changes. So particularly over voltage is due to abrupt load rejection. Suddenly, if any load is removed. So series parallel harmonic resonance cases, sudden line to ground faults, improper earthing schemes, poor voltage regulation throughout the system, overcompensation of the reactive power support provided by the capacitor banks. So if more capacitance is added, so then also in order to compensate the dropped voltage, so instead of acts as a voltage regulator up to the rated volt, so this voltage is going on increase, right? So whereas under voltage issues, an increase in the system losses and results in voltage stability problems, motor starting problems, protection relay tripping. So these are the various reasons for the over voltage and under voltage problems. So one more thing, we are having balance. So unbalance, generally balance, you can find it in three-phase system. So voltage unbalance is an important power quality issue that can be defined as a condition in a three-phase system in which root mean square magnitudes and phase angle of the fundamental component of the phase voltage are not equal. So here we are expecting all the phases should be properly balanced. So otherwise, if this magnitude or phase angle, if these are varied from one phase to another phase, it comes under voltage unbalance. The principal reason of voltage unbalance in a system is the unbalanced loads. This asymmetric loading causes unequal phase currents to flow through the electrical network and causes unsymmetrical voltage drop on system feeders. So all are what we are discussing according to IEEE standard only. Similarly, voltage sag. Already we discussed about under voltage and over voltage. Under voltage, over voltage is different from voltage sag and voltage swell. So voltage sag is defined as reduction in the RMS voltage. So the reduction also from 0.1 to 0.9 per unit for a period of 0.5 seconds, 0.5 cycles to 1 minute. So our voltage usually, which is if it stays for more than 1 minute, the problem, then it is said to be over voltage. But whereas here the time boundary is from 0.5 cycles to the 1 minute. So whereas the magnitude also clearly mentioned according to IEEE, it is from 0.1 to 0.9 per unit. Whereas voltage sag can be characterized into three types according to its time duration: instantaneous, momentary, and temporary. I mean, how long they stay, whether it is for 5 cycles or 10 cycles or 1 minute. So voltage sag results from sudden system faults and switching events of larger loads having excessive starting current, such as large motors. Anyhow, voltage sag is nothing but it is so if the reference voltage or the rated voltage for the consumer side, maybe if it is between 0.1 to 0.9 per unit, so if it lies from 0.5 cycle to 1 minute, then it is said to be voltage sag. Whereas voltage swell, it can be defined as a rise in the root mean square voltage for periods that ranges from 0.5 cycles to the 1 minute of time. So here the time remains 0.5 cycles to 1 minute. Swells are usually produced by electric faults like LG fault, upstream supply failures, heavy load rejection events, and switching of shunt capacitor banks. Voltage swell is categorized according to time duration into three types, which are instantaneous, momentary, and temporary. Whereas one more thing is there, interruption. So interruption is a random event which occurs with zero magnitude voltage or current for a particular time period where the magnitude of voltage or current is less than 0.1 per unit. We have the different standards. We are saying that sag, swell, under voltage, over voltage. So everything is starts from so sag starts from 0.1 magnitude. So if it is below the 0.1 per unit, whether it is a voltage or current, it is said to be interruption. Whereas according to IEEE 1250, the electric interruptions can be categorized into four types. So we already discussed in the previous slide. So whether it is instantaneous and momentary and temporary or sustained. So if the problem is instantaneous, means so it is between 0.5 cycles or it may end at 30 cycles. Momentary means the duration starts at 30 cycles and duration ends at 2 cycles. Whereas temporary means 2 cycles and duration ends at 2 minutes. Whereas sustained problem means it is longer than the 2 minutes. So this is the we discuss. So as we already know, the different we covered over voltages, under voltages, harmonics, unbalanced, sag, swell, transients, interruptions, frequency deviations. So interruptions as well as frequency. So there will be frequency deviations. So we are expecting the system to be Indian standards saying that the frequency should be at 50 hertz. Whereas if it is more than or less than the 50 hertz, so if it is then there should be a deviation in the frequency. So we can observe the light flicker. We can observe the flickering of light, that is incandescent lights. Sometimes they are going to be flickering. Now let us move to the actual part. What I want to convey at this time, that is harmonics. Harmonics are sinusoidal voltages or currents having the frequencies that are whole multiples of the frequency at which the supply system is designed to operate maybe at 50 Hz or 60 Hz. So we are having, so if the frequencies are multiples of the fundamental frequency means Indian standards we are following 50 Hz. Suppose if the frequency is 100 Hz, then it is a second order frequency. Whereas if it is at 150 Hz, it is a third order component. Suppose if it is at 250 Hz, then it is said to be fifth order harmonic. So we all well knows about the harmonics. So there are interharmonics also present in the system. Nowadays, these interharmonics are causing various problems in the power system. So what are interharmonics? The IEEE defines interharmonics are a frequency component of a periodic quantity that is not an integer multiple of the frequency at which the supply system is operating. Whereas IEC defines between the harmonics of the power frequency voltage and current, further frequencies can be observed which are not an integer of the fundamental. They can appear as discrete frequencies or as a wide band spectrum. We all well knows about 50 Hz system and 60 Hz system. So what about 90 Hz? What about 120 Hz? What about 130 Hz? So these are said to be interharmonic components. So multiples are called simply first order is 50, fundamental frequency is 50, second order is 100, third order is 150. So likewise, we are saying that harmonic number is there. But there is other frequency components to appear in the power system. So those are called interharmonics. We are also having the subharmonics also there. So subharmonic frequencies are frequencies below the fundamental frequency in a ratio of 1 by nth of the fundamental frequency, where n is a positive integer number. In other words, the subharmonics are the fractional frequency components. So for our fundamental, so Indian frequency is about 50 Hz at standard. So if it is 1 by 2 into 50, that means 1 by n into 50. 1 by n refers to, so n refers to 2 or 3 or 4 or 5. So if it should be less than 50 Hz, less than 50 Hz means it is minimum of 1 by 2, 1 by 3, 1 by 4, 1 by 5, like this. So these are called subharmonics in power system. So this 50 Hz is the fundamental frequency, subharmonics are, this is the subharmonics of the, this is the understanding purpose I have represented here. So from these two slides, I just want to convey one more again. So fundamental frequency is at 50 Hz. So above that, if it is not the part of the multiples of fundamental frequency, and if it is more than the fundamental frequency, it is said to be interharmonics. Whereas subharmonics are less down the, if it is less than the fundamental frequency, which is this order is 1 by nth time of the fundamental frequency. So further simple explanation I would like to bring to you. So here, this is the pure sinusoidal wave, let it be at 50 Hz. A 250 Hz sine wave signal, which is superposed onto the fundamental 50 Hz main supply, will be designated as the fifth order harmonic or as the harmonic of fifth order. Any signal component having a frequency which is not an integer multiple of the fundamental frequency is designated as an interharmonic component or referred to more simply as an interharmonic. So harmonics and interharmonics are basically the result of modern developments in the electricity utilization and the use of electronic power condition modules. So using switching power supplies to control loads and to reduce power consumption results in unwanted frequencies superimposed on the supply voltage. So the presence of voltage at other frequencies is as far as possible to be avoided. So by observing the diagram, so this is the 250 Hz component, whereas this is the 50 Hz component. So before discussing what are the main sources of these harmonics, we must I just want to give an introduction to the linear system once again. So linear system, the main source of the harmonics are nonlinear loads. The main source of these harmonics are non-linear loads. So linear loads, example, let us consider a resistor as a load. So that volt current ampere characteristic lies on the, so they have no phase difference, and they are meeting at the same instant of time, so that there is no phase difference. Even though inductor and capacitor also, they are making an lagging and leading power factor, and they are varying they are varying same instant with respect to their phase difference. So the characteristics of the voltage and the current are sinusoidal in nature. The current contains only one frequency. The main frequency, also called fundamental. Beside the presence in the system. What about the nonlinear load? So this is the main source of these harmonics. In opposition to linear loads, a nonlinear load changes its impedance with instantaneous applied voltage that will lead to a non-sinusoidal current draw when the applied voltage is so. In other words, the kind of load doesn't have a constant relationship between current and voltage along the alternating period. The simplest circuit to represent a nonlinear load is a diode rectifier with its multiple variants like full wave rectifier, half wave rectifier, single phase or three phase. Okay, so some examples for nonlinear loads are capable of injecting harmonics into an electrical distribution or industrial equipments, that is welding, arc furnace, variable frequency drives, line switching rectifiers, switch mode SMPS, switch mode power supplies, lighting ballast, and also modern electronic equipment at low load level. Even they could be designed to optimize efficiency around its rated working point. So all these circuits can contain semiconductor power devices such as diode, thyristors, transistors. So main source of this nonlinear load is the main source of harmonics is only due to nonlinear loads. So this diagram will give us a clear understanding about the nonlinear load concept. By taking at the point of common coupling, so these loads are going to be connected. So here by taking this load, so whenever it is this is a rectifier. So whenever it is activated by the 6 pulse circuit, so this 6 pulse rectifier and is highly distorted current draw. So here actual voltage, actual supply voltage is V phase is this one. Whereas output is varying, the output is going on changing like this. IPH1 refers to the so distorted, and it's the highly distorted current, not proportional to three phase supply voltage. Red color so this is said to be the output current. So what you can say is we spent 50 hertz signal here, but the output is not a 50 hertz signal. So with this the result of these harmonics will be again it is going to be impacted. This will again be source of the supply. We already discussed the potential sources are switched modes, power supplies, dimmers, current regulators, frequency converters, voltage source inverters with pulse width modulated converters, low power consumption lamps, electrical arc furnaces, arc welding magnetizing current associated with saturated or saturation of the iron. All equipment with built-in switching devices are with internal loads with nonlinear voltage current characteristics. So these are the main source of harmonics. What are the effects of harmonics on main supplies? So distortion of main supply voltage, unwanted current flowing in the supply network generate additional energy losses. So we are having actually these losses include I square R losses. So once these harmonics are injected, so that these losses are proportional. The losses, if the losses earlier was I RMS square into R. So after injecting this, so the losses will be the function of the harmonic currents also. That is total harmonic distortion. So that losses are going to be increased. So defective operation of regulating devices, disturbed operation of fluorescent lamps, television receivers, or other equipment, and malfunction of ripple control and other main signaling systems, protective relays, possibly other control systems, and you can find additional losses in capacitors and rotating acoustic noise from motors and other apparatus, reducing the efficiency of motor. So this is you can find telephone interference. High harmonic amplitudes may not only cause malfunctions, additional losses and overheating, but also overload the power distribution network and overheat the neutral conductor and cause it to burn out. So these are the various effects of harmonics on the supply. However, we need to discuss about the standards. These standards are very important. What are the international standards? What they are saying about the harmonics? So IEEE as well as EN 50160, these are the two different standards. So EN 50160 specify the standards for voltage variation, flicker, unbalance, harmonic voltage, main signaling voltage, whereas IEEE which specify the voltage and current harmonics up to 161 voltage. So by the IEEE, according to IEEE 519, 1992 and 2014, so bus voltage at point of common coupling. So here, so voltage distortion, percentage of voltage distortion, and if V is less than 1 kV, maybe 3-phase or single phase in India, so individual voltage distortion should be 5%. Right. So whereas THD, they are expecting 8% of THD, that is total harmonic, total voltage distortion. That is in voltage, harmonic distortion should be 8% is accepted. Whereas from 1 kV to 69 kV, so according to the individual voltage distortion should be 3%. Whereas that is according to 2014, so individual voltage distortion, this is total voltage distortion should be 5%. Whereas from 69 to 161 kV, so THD should be 2.5%. More than 161 kV, like 400 kV or 220 kV, so that should be between 1 to 1.5%. Whereas this is very much required. This is about current harmonics. So short circuit ratio by this is the current distortion limits for systems rated 120 volts through 69 kV. So ISC by L, that is short circuit ratio, the ratio of short circuit to the maximum fundamental load current. So this is the harmonics accepted, that is TDD refers to total demand distortion. So THD, we all know THD refers to one cycle or two cycle or couple of cycles. Whereas TDD, if you want to check it for more cycles, surely it will call the particular time period. Surely it will be called demand TDD, total demand distortion. So for different ratings, that is, but between if it is more than 20 and if it is less than 50, so that so it is order of harmonics should be order harmonics should be like this, and individual harmonic order also mentioned. This is according to IEEE. And the current distortion limits for systems rated above 161 kV according to 1992 and 2014 data. So demand, so this order of harmonics should be like this. So by seeing the above results, recommendation for increasing current limits to reduce lower order harmonics. So we need to, so the multiplier is required to mitigate harmonics order limited to 25% of value given below. So when you consider this multiplier like 1.4, 1.7, 2 and 2.2, so that harmonic orders can be limited. So whereas IEEE standards are different from Indian standards because Indian standards are not constant. So Tamil Nadu, so Gujarat state, it is saying that 5% with single harmonic content not exceeding 3%. Likewise, each state having their THD values are not uniform. If you observe Andhra Pradesh, cumulative THD should be 3%. So whereas here in Karnataka, more it should be around 4. It is 4% and 9%. Likewise, the uniform pattern is not observed in the various states. So here, according to CEA, THD with 5% with single harmonic content not exceeding 3% for 33 to 132 kVA is accepted, whereas THD of 2.5% with single harmonic content not exceeding 2% for 220 kV, whereas for 400 kV, 2% with single harmonic content not exceeding 1.5%, THD with 1.5% with single harmonic content not exceeding 1% for 765 kV. So these are the authority of electricity. So they said these are the different standard according to the Indian voltage regulations. So these are the IEEE as well as Indian standards. In this slides, we would like to discuss the harmonic measurements. So measuring the harmonics also very important task. Usually we are having two methods, that is non-parametric. So this is according to elsewhere. So this paper brought it from. So this is a letter survey paper. So I got good information from this paper, because if any research students are there, surely you can go through this paper. So harmonic is generally estimated by using two methods. One is non-parametric method and parametric method. So non-parametric method, surely it must have the standard formula. Like, so we are having the mean, or we need to calculate from standard deviation. Okay, or so we must have the function and we must have the expressions. So here frequency domain analysis. So non-parametric methods includes frequency domain analysis. One among that is discrete Fourier transform, and time frequency domain analysis. We are having wavelet transform, Hilbert-Hung transform, Chip-Jet transform. So whereas parametric method, so in parametric method there is these are varying. There is no standard format, right? So this format is not standard, and functions are varying. So this parametric method, we are having sinusoidal models and stochastic models. So in that we are having different methodologies are there. Anyhow, our focus is on our focus is on non-parametric approach. Of course, many research is going on in parametric methods too. So before discussing the different methods and their comparison, we would like to discuss briefly about THD. So total harmonic distortion can be defined as, so this is harmonics can be represented as square root of sigma n is equal to n to n is equal to n in by I1 whole square. So since fundamental frequency is not the part of the harmonics, so that it is not considered, and it starts from second order. So whereas RMS value, we know RMS value is nothing but it is sigma n is equal to 1 to n square, and harmonics, total harmonics can be represented, can be defined in terms of IRMS to fundamental. So that is equal to IRMS by I1 whole square minus 1. And IRMS is equal to I1 into 1 plus THD. So why I am saying is, so once these harmonics are injected, so no longer be these losses will remain. Earlier the losses are with respect to the I1, that is fundamental current I1 square into R. Whereas once these are varying, so these are transformed to IRMS, and they are became I1 into square root of 1 plus THD high whole square. Similarly, it is true in the case of voltage harmonics also. So the harmonics remain same. We need to calculate both in voltage as well as current also. In the case of voltage, it will be n is equal to 2 to n Vn by V1 whole square. So here, in the presence of harmonics, the expression of active power, reactive power and apparent power need to be defined carefully. So the displacement power factor cos phi is due to the phase shift between the voltage and current of the frequency F1. So here, earlier, I mean, before the harmonics are injected, power factor is became P1 by S1. So active power of the fundamental and S1 refers to the apparent power of the fundamental. Whereas once these harmonics are injected due to the problem, so that power factor remains P by S, where P remains active power considering the harmonics and phase displacement between voltage and current. Similarly, so this power factor became P by S, and where P is equal to sigma n is equal to 1 to n Vn In cos phi n. Right. So S is equal to, where S is equal to P square plus S, usually S is equal to square root of real power and reactive power. Whereas, so there is a one more time, that is distorted power also to be considered. So thereby, so the power factor will become cos phi 1 by square root of 1 plus total harmonics. What I want to convey is the impact of harmonics is not only in the other part of the system, which you can be seen as a heat or other problems. It will be on the power factor too by observing this diagram, by these expressions. So according to the survey paper, so we are having FFT, that is fast Fourier transform, which is simple and fast. Demerits are there like leakage and picket fence effect, aliasing, time of information is lost, hence cannot detect transients. Potential application, stationary and linear signal with constant fundamental frequency. Whereas by adding some window feature, WAFFT is taken, reduces spectral leakage, easy synchronization of data, and we are having discrete wavelet transform, wavelet packets. Likewise, so these are the various, this is the data regarding the measuring the harmonics with different parametric and non-parametric approaches. Right. So these non-parametric approaches, they are good advantages. So what are the, finally we will talk about the mitigation techniques. So the prevention of even and odd harmonics from electrical system to get pure sinusoidal wave. So due powering and grounding of an equipment in a matter which is suitable for the appropriate operation of equipment and other interconnected equipment. So coming to the harmonic mitigation methods, so segregation of harmonic producing loads from sensitive loads and use of star delta transformer and optimal usage of variable frequency drives and soft starters, optimum selection of generator pitch factor and harmonic. So there is a provision for mitigating the harmonics by AC line reactors, DC line reactors, K factor transformers, multi-pulse drive configuration like 6 pulse, 12 pulse, 18 pulse, 24 pulse, passive harmonic filters, active filters, and hybrid harmonic filters. So this is about harmonics, how these power quality. Up to what I discussed is what are the different power quality problems, what are mean by harmonics, what are the how do you express the formulas for harmonics, and what are the different methods. What are the different methods to calculate the harmonics, and what are the previous research that was made on measuring the harmonics. So here case study. So this is the work which I taken from IEEE. So this is so when the source is connected to non-linear load. So non-linear load is simply it is made up of a full bridge rectifier. Let it be non-linear load in the sense it is a full bridge rectifier. So where we are having the point of common coupling where where the load is going to be met. So in the starting I am having this wind farm and non-linear load is there. So whenever this wind farm is connected, when the wind farm and nonlinear load connected, then the impact is on the main power source. That's what I said to you. So these harmonics which are produced on the load, or the harmonics which are injected in the load, so they are not meant for the load itself. So again they are supplied to the source side, so our grid side, so that here due to the presence of the load, so these harmonics will be produced on the grid. So to mitigate these harmonics, I have used the StatCom. So this which is based on a simple controller. So this by using this simple controlling topology, I have reduced these harmonics. So this is the voltage while coming to the parameters of the test system. So this supply is at 3-phase 415 volts 50 Hz, and the generator specifications. So we are having this. This is the different parameters of the test system. This is the MATLAB Simulink model. A three-phase system, one nonlinear load is taken, right? So here, so this nonlinear load, whenever this nonlinear load, due to the effect of connecting this, and harmonics are incorporated onto the load side, right? So to mitigate the harmonics, I have used this StatCom based on hysteresis current controller technique. So while coming to the topology which is used in the StatCom, so here I have got the actual values and reference values. Based on the actual values and reference values, so this hysteresis band is obtained. Based upon this hysteresis band, if hysteresis band is there, then SA is equal to 1, which means that then the signal is sent on to the controller. So accordingly, the signal is going to be obtained. Whereas this, if hysteresis band is less than ISA minus ISA star, then it will not present, that is 0. Then you will not get any input to the current controller. So here in a three-phase balanced system, the RMS voltage source amplitude is calculated at the sampling frequency from the source phase voltage VSA, VSB, and VSC. So here VSA, VSB, VSE are expressed in terms of USA. So this is the expression for USA, USB, and USC. So the in-phase generated reference currents are derived using in-phase unit voltage template. So finally, so here the output is going to be obtained based on the actual value and the value obtained from the ISA star. ISA star is equal to I into USA, ISB star is equal to I into USB, and ISC star is equal to I into USC. So if these are if the difference obtained, then hysteresis band, then output will be presenting. Coming to the results, so before connecting the StatCom, so these harmonics are injected onto the line like this. So once this StatCom is connected with the help of hysteresis current controller, then the harmonics got reduced. So these harmonics got reduced, and these harmonics will be reduced. And by comparing the harmonics, without any compensating device, we got the results about total harmonic distortion is about 27.04. Whereas by using the StatCom, we got only 2.89 percentage of the harmonics. So usually in MATLAB Simulink, I think most of the students well knows about this concept of measuring the harmonics. In PowerBI, we can find FFT analysis. So if you once click the FFT analysis, then you can find the block like this. So here usually we need to hear what is the name you specified in the MATLAB Simulink. So that name will appear here. So suppose output voltage is VO, so it will comes like this, and so this is the signal. Start time. I mean, the particular problem sag may occurs at 0.2 and ends at 0.21 or something. So you need to calculate, if you want to calculate the harmonics at the only at the instant of time where the sag occurs or where the harmonic occurs, so that the time is going to be started at that instant. So number of cycles, so depends upon your problem whether it is a one cycle or two cycles, so you need to check it. And fundamental frequency, I have taken actual 50 Hz, so this is only for understanding purpose. I am showing this slide. So fundamental frequency, you can fix it. So this is where after getting this, you can find this is the wave where I have taken. So a particular wave ఎంత వస్తా ఉంది, harmonics ఎంత అనేసి clear గా వస్తా ఉంది. So here this is only for understanding purpose. I have shown how to show the harmonics in power guide plot can be represented like this. So here the order of the, so these bars will indicate that, so what is that order of the harmonics and what is the percentage, I mean the magnitude percentage of fundamental component will be seen here. So again, our work has continued to calculate the harmonics by using wavelets also. So up to now, what we have seen is we are used to measure the harmonics only with the help of FFT. So since FFT it is a in frequency domain. So in order to improvise the accuracy, because what is the order of frequencies we can see from the from the FFT analysis. So whether it is a first order or second order or third order. So if it is only the order of the if the order lies in the band, then only it will compute. Suppose my question is, I have got some, so 50 Hz is the fundamental frequency, some 60 Hz or 70 Hz. So all these will not comes under the harmonic bands, and this FFT analysis will not consider the particular marginal values. So we made an attempt here for measuring the harmonics with the help of wavelets. So here this is the the harmonics, or this is the actual wave which obtained. The first wave refers to the actual wave, and this is the approximate value. This is the approximate coefficient, whereas detailed coefficient. So this is done in 5 level. So that detailed coefficient in first level, second level, third level, fourth level, fifth level. So these the coefficients. So these approximate coefficients or detailed coefficients are very much required to know the extreme characteristics of the particular wave what you are analyzing. So in that motto, so here this is the detailed coefficients of source current at level 1 without any controller here. So this is also without any compensator. So this is the detailed coefficient of source current at level 1 without any controller. Similarly, this is the detailed coefficient of source current level 5 without. So there are a coefficient called I have the other waveforms like detailed coefficient of source current at level 2, level 3, level 4, and level 5 too. So by knowing the data, so detailed coefficients at level 5 with by connecting the StatCom, so I got the values, approximate value and detailed values with StatCom also. So this is approximate coefficient at level 1 with StatCom and detailed coefficient at level 4 with StatCom. So we brought the values from level 1 to level 2, level 3, level 4, level 5. Okay, so here mother wavelet what we used is Bayer 3.3 at level 5, and the analyzed information is detailed coefficient at source currents, and sample frequency is about 1500 kilohertz, and actual frequency is 50 hertz, and number of samples we computed for this attempt is 30,000 total sample have been tested. So this harmonic measurement is a big task, because number of papers from elsewhere and IEEE, there are a lot of attempts, and they have been there are of various papers on various expressions have been proposed. So I have taken a standard paper and IEEE and elsewhere. So here total harmonic distortion can be represented it is the square root of sigma j is equal to 1 to m 2 power j power minus 1 into sigma k is equal to 1 to n j d j whole square k by 2 power m minus 1 into sigma k is equal to 1 to nm a m square k. So here, what is this dj and am? So d for detailed coefficients, a for approximate coefficients. So I have already taken, I am having the approximate coefficient and detailed coefficient. First level, I have first level coefficient, second level coefficient, third level coefficient, fourth level coefficient, and fifth level coefficient too. So by summing up these detailed coefficients and approximate coefficients. So m is the number of decomposition levels. I mean, so here 5 level decomposition has been done. djk is the detailed level at level j. So here, so what is the detailed coefficient in level 1, detailed coefficient in level 2 up to level 5. So am of k is the approximation at level m. So approximation takes place, and k is the coefficient number at level j, and nj refers to number of coefficient level each level j. So I have computed this after getting the approximate. I have gone through this and I have gone through the programming so that our analysis we computed the harmonics with the help of wavelets too. So where the 27.04 from FFT analysis and THD by using wavelet MRA is about 28.5, and with StatCom 2.89 and 3.20. So from the earlier slides, what I just want to convey is, even though it is basic talk regarding the harmonics, just I want to make an attempt to reach you with the help of what are the different types of harmonics available, like harmonics, subharmonics, interharmonics. What are the different reasons? What are the different techniques which have been used to measure the harmonics, like parametric approach and non-parametric approach? And I have taken a simple case study. So I already mentioned to you, we are having a lot of techniques to measure the harmonics, but we are very much familiar with FFT analysis. Anyhow, so we are having our methods too. So to compute the harmonics, so we attempted, and I have evaluated I have given the summary of the case study also. So this is about the overview of the harmonics, and so the effect of harmonics and overview of the harmonics. Thank you for giving this valuable opportunity.
Thank you, sir. Thank you for giving the brief discussion on harmonics and their impact on peak to power quality, and how to mitigate harmonics replacing patch devices, and also explain wavelets. So thank you very much, sir. All these things will be useful for us for our research. Thank you very much for accepting our request. Now, dear participants, hope you have enjoyed the session, and now you are open to raise any queries.
Yeah, good afternoon, sir. This is Popita.
Yeah.
Sir, in the StatCom based inverter, like how you are controlling, sir? Like hysteresis controller you have taken for StatCom controller, sir.
Yes, madam.
But can I take any SBM space vector modulation technique like that, or what is the difference, like, sir? Like in StatCom based inverter, I am using SBM, sir, space vector modulation technique. And this is other technique or what? Hysteresis controller you are using?
Madam, StatCom is a device. So you know, we are all know it is offering good opportunities. So where the controller is required, according to our problem, so controller is going to be designed. So here hysteresis current controller, I have taken the band where to operate. So for your problem, you can design your own StatCom. So maybe different methodologies are there, like fuzzy controller or artificial intelligence, different artificial intelligence controllers. So I have used only basic control. This is a basic controller, madam. It is. I don't think that this is where simple expressions are just required, and depends upon those simple equations enough. I can have designed, madam.
Okay, sir. Thank you, sir.
It's a madam. I had good question, madam. My suggestion towards these controllers is we are having a lot of research papers and survey papers, madam. If you go through any survey paper, literature survey paper, it gives us different control topologies available. Particularly for the problem, maybe what I case study is about harmonics, but my case study may be changed from harmonics to some maybe other problem. Okay, whatever it may be, stability problem. So whatever it may be, so my suggestion is, so we are having different topologies and different topologies are there. If you go through it, it will gives you a good idea, madam.
Okay, sir. And sir, how you are sizing the components, sir? Like the rating, how you are deciding? Mathematical calculation is there or what, sir? Or directly you have taken?
Madam, we are having mathematical calculations. Along with it, so some values can be, so directly taken, and some values can be random taken, and mathematical solution also required. For this, madam, I will send. Please ping me mail, madam. On base paper is there. So what are the different methods and how the ratings can be evaluated, which gives you clear idea on that, madam.
It will be fine, sir, because my research area is in this way, subject only.
Yeah, I know, madam. I got it, madam. So I have one paper related to all the parameters, how they have to be chosen. I will send it to you, madam.
Thank you, sir. Thank you.
Thank you, madam.
Any questions from other participants?
Okay, thank you, sir.
1 minute, sir. No questions from any participant. We can close the session now. Any participants have doubts, you can raise. Okay, sir. Thank you very much, sir. So today we are closing the session now. Thank you all. In few minutes, I will send you. We will send you the feedback form, or if you fill that form.